Hello, everyone. I am Philip, and I'll be there as tech support during the tutorial. I want to introduce to you our tutor, Christophe Zoghbi. He is a founder and CEO at Zaka, and he will hold the Build Your Own AI chat box with OpenAI and LangChain tutorial. Enjoy.
Thank you, Philip. Hello, everyone. Give me a second to share the screen. Get started. So my name is Chris. I am basically the tutor for this session. A quick background about myself. I have more than 14 years experience in software development. So I'm coming from a software engineering background. I got involved in artificial intelligence, I think 8-9 years ago. And I've been working in AI ever since. Initially, I was an AI engineer building projects, and then I realized that there's a lot of need to educate people on AI. So AI education is pretty much needed, everywhere in the world, and that's why I decided to build Zaka, my current company that focuses on AI upskilling and educational programs. So today's topic is about building your own AI chatbot using OpenAI and LangChain. So we've all seen the last year how crazy that was, especially with the release of ChatGPT. And we've had chatbots for a while, but ChatGPT kind of gave us another push towards that field. So everyone's now excited about building their own smart assistants, chatbots, etc. So let's dive into that. If you have any questions throughout the whole presentation and the workshop, please ask it in the chat, and I'd answer it right away. So before we get started talking about OpenAI, I wanted to kind of give you a quick background about chatbots, right? So where are they? Where are we currently? And what's the situation when it comes to chatbots? And as I said earlier, chatbots are nothing new. We've had these assistants for quite some time. If you think about Siri, if you think about Alexa, these are some virtual assistants that we've had for more than 5-6 years now, maybe even more. And they're part of our everyday life. We ask them questions, we ask them to do something for us, and they understand our request, and they usually respond back. And so if you think about it, how does these machines communicate with us? How do they understand what we tell them or what we ask of them to do? And it's basically because of the field called NLP, or natural language processing. So NLP is, again, natural language processing. And if you want to talk about what is NLP, we should define what is natural language, the NL part of NLP. And natural language is the language that humans use to communicate. So right now, I'm speaking with you using the English language, and this is called a natural language. So a natural language can be either speech or written text. So these are two ways that we use natural language. And when we build machines to process and understand these natural languages, then we are talking about natural language processing. So NLP is the field that allows machines to process, to understand, and to communicate with humans using natural language. That's kind of the idea. So you might be thinking, okay, what can I do with NLP? You can do machine translation. So you can build models that can translate text from one language to another. You can extract information from documents, which is called information retrieval. And a big example of that is Google search. If you go to Google and you write a couple of words, automatically the engine understands your query and looks up information based on your query. It doesn't look key by key or specific words like it used to back in the days. It actually understands the whole query and gives you relevant information. And that's why, or that's how AI is used in information retrieval. We can also do question answering. We can also do sentiment analysis. There's a lot of tasks that we can do using NLP. But the goal is not to see what we can do, but actually to understand how this works. So you might be thinking, how does this whole thing work? So let's play a small game to tell you how it works. Imagine I give you the following sentence and I tell you, fill in the blanks. Okay, I went to the blank to buy some blank. What would you guys fill in those missing words? Automatically, I'm sure you guys already have some ideas of how you can fill in this sentence. And the idea is because when you read the words I went to D, you know that this word has to be a location, right? It has to be a place. I went to something. I go to a location, and then to buy some whatever, some stuff. So you might say, I went to the mall to buy some stuff. I went to the store to buy some groceries. I went to the shop to buy some books, whatever. So there's a lot of different options, but all of us know how to fill in the blanks. Why? Because we understand not only words and their meaning, but we understand them in context. So where does every word fit into the sentence? And if I want to build an AI that understands these kind of things, we call this a language model. So a language model is a AI model that understands a certain language, that understands not only the meaning of the words, but how these words are correlated together. So how do we get this language model? Well, of course, we train it. Just like we do everything in AI that way, we train a language model. So if you know anything about machine learning or AI in general, we get data, we feed it to an algorithm, it gives us a model. Same thing happens here. We take lots and lots and lots of training data. We feed those data to a language model or to a machine, sorry. And the machine, the algorithm, builds a language model based on the training data. And in this case, we're talking about articles from the internet. We're talking about newspapers, blogs, Wikipedia pages, comments, you name it. Anything that's written and that's online, we can take it and we can feed it and we can learn, or we can teach a model to learn the language from those data. So the way that the language model is learning is that it looks at the words and how frequent these words come together. So if there's a word that comes always with another word, somehow these words are correlated. Or if there's a word that always comes in the place of another word, also these are interchangeably correlated. For example, the model will learn that the word yellow and the word red and the word blue and the word black and the word white are somehow correlated. It doesn't know that these are called colors, but it knows that somehow these words are correlated, because I can say I bought a yellow car, or I bought a red car, or I bought a blue car. So I can remove or change these words and the sentence would still make sense and would still be a valid sentence. So whenever these words appear in a similar context, then somehow they're correlated. So of course, this is a simplification of how these models are learning, but the idea is that we don't give them any answer, we just give them text, they read a lot of these texts, and then they understand the language based on that text. And again, we're talking about huge amounts of data, right? Not just a couple of texts, we're talking about millions, if not billions of text documents. So once the model learns these correlations, then the way it works is that it can fill in the blanks. It can continue a sentence, for example, by predicting the next word that should come in that sentence. And the way it does that is by predicting a probability. So what is the probability of that word to appear after those words in this sentence? Okay, that's kind of how it works. So for example, if I have a sentence that says the roses in the vase by the door, and then I have, let's say, two options, is or are, two words that can compete, then it calculates the probability of every word, the probability of the word are versus the probability of the word is. And because we are talking about roses, so the plural form, then of course this probability is higher, and then we go with the word are. And then same concept, right? So if I want to show you an example, look at this animation. We are filling in the sentence one word at a time by predicting the next word. So we start with the cat, then we select the word sat, for example, and then on, etc., etc. And you can see the probability, right? The number next to every word. And the word with the highest probability is the word that is chosen to fill in the blanks. And that's how technically ChatGPT, for example, answers us, or any other language model. We give it some text and it starts to formulate the text one word at a time. So word after word, it forms sentences. And then sentence after sentence, it forms whole paragraphs and the whole answer. And that's exactly how large language works. Any questions so far? is this idea clear? If you have anything you want to add, you can write it in the chat or submit a question. I want to make sure that you guys are understanding the concepts as we proceed. So you might think that language models are basically something that ChatGPT was something that was new and we just saw them, but actually we've had them since the 90s. They're nothing new, right? We used to call them statistical language models because they use statistical machine learning algorithms. Then we started using deep learning algorithms or neural networks, and then we called them neural language models. And then in 2017, there was a paper that was released by some researchers at Google that introduced a new architecture that we call transformers. So transformers is a revolutionary, let's call it, architecture of neural networks that allowed these language models to be very efficient at processing and understanding text. I'm not going to dive into the technical details of how transformers work and why are they efficient, but you should know that from that point onwards, we've had a breakthrough in NLP models. So in 2018, we had a model called BERT by Google, and also a model called GPT-1 by OpenAI. In 2019, we've had GPT-2. In 2020, we've had Lambda and GPT-3. So these are some of the large language models that we've had released. And of course, if you look at the landscape of all the large language models released from 2019 until today, there's a lot and a lot and a lot of them, right? So Google has models, OpenAI has models, Baidu, Microsoft, Hugging Face. You can see lots of different, Amazon, Meta. So every big tech company basically has its own large language model, right? So it's not only specific to ChatGPT or these most famous ones. So this brings us to actually OpenAI. Okay, we all know OpenAI. We've all heard of OpenAI. It's this company that actually, especially after this very heavy weekends, I'm sure all have heard of what's happening at OpenAI. So if you don't know what OpenAI is or what they do, they are the company behind ChatGPT and the whole GPT models. And of course, they have also an API. So if you'd like to use GPT models in your application, you can use their APIs, and basically they give you the option to understand or to generate natural language and to generate code as well. So you know that you have LLMs that can write code. You can also create or generate images with them. So yeah, they have a model called DALL-E that creates images, and they also have a speech-to-text model that can convert or transcribe speech into written text. So their libraries are available in different languages, from Python to Node.js, etc., etc. And of course, they have different models such as GPT 3.5, GPT-4, the DALL-E models, etc. So of course, you can find all of them on their documentation page. But today, we will be focusing on GPT models and on basically building chatbots using those models. So I would like to explain a bit how ChatGPT works and how GPT models actually work, because we have to make a certain distinction here before we dive into the topic. And there's a great talk. If you don't know who this guy is, his name is Antika, and he's a great researcher in the field of AI. He gave a talk at the last Microsoft event called State of GPT. And really, I encourage you all to watch this talk because he explains greatly how these systems work. So I tried to take a couple of screenshots from his talk and to explain to you the different steps that are involved in building a large language model and also in building a ChatGPT assistant model, because there's a bit of difference between a static LLM and a assistant chatbot like ChatGPT. So hopefully I will make this this clear for everyone. And this is one of the screenshots I took from his slides. Again, if you have any questions on this, please interrupt me and ask. I would like this to be very clear to everyone. So basically, there are 4 different stages from starting from scratch to actually getting to a ChatGPT level model. The first stage we're going to focus on is called the pre-training stage. And this is where we use raw internet data. So lots and lots and lots of data. We call it large quantity, low quality. We just scrape the internet, collect all the articles that we can find, all the Wikipedia blogs, books, whatever it is, comments, etc. And we put them all, feed them into a neural network to basically model that language. So this is where the language modeling is happening. And this is where it's an unsupervised learning mechanism where the model is learning to predict the next token in that sentence, right? So I just get the data, I feed it, I say, here, learn this data. And the model learns to predict the next token. And it gives us a base model. So notice how we said here, predicting the next token, because technically speaking, when we talk about LLMs, they don't actually process words as they are, they process tokens. So there's a process that we call tokenization, where we convert text into tokens. So every tokens are just numbers, right? So every word, or sometimes a piece of a word, can be divided into a specific token. For example, here, the dog eats the apples. The word the has token 464. The word dog has the token 3290. Eats has a different token, the etc. etc. Right? So if you'd like to play around with this, there are a couple of links that I kept here. This is one of the interesting websites where you can actually visualize. Okay, just a second. You can visualize tokens. So if you write, like, say here, I'm going to say, hi, my name is Chris. Okay, so you can see the tokens based on my text. So hi would be that token, my, etc., etc. This is basically how you can convert text to tokens, or you can convert tokens to text. So if I write here 17250, that would be hi. If I write here 615, that would be AV. 616, that would be space my. So there's a certain way to encode these words into different tokens, and we're just using here the GPT-2 tokenizer. You can also search all the tokens. You can see, for example, the integer value for every token. So capital C is 34. So if I write here 34, you can see here capital C, right? So just a way to map all the words together. So going back to our presentation, as I was saying, before we can feed the text into the model, we have to tokenize it. We have to convert it into tokens. And that's why after the model learns to predict the next token and then eventually convert it into words. And the output of that phase is a base model, right? So it's a model that we call it a base model, where it can learn to predict the next word. And this type of training requires thousands of GPUs. It's a very, very, very expensive process because we need lots of GPUs and lots of time to train those systems. So that's why you hear about these companies using, multi-million-dollar infrastructure training, systems across weeks, etc., etc. So the output of that would be a model like GPT, like Llama, like Palm, what we call a large language model. And this model can be deployed, right? We can use it to continue or to complete the text. So this is basically how the pre-training works. So after we convert it into tokens, we then have a certain sentence, and then we teach the transformer, the architecture, to predict the next token. So you can see here we have a token context, which are the yellow tokens, and then green is the currently highlighted token. So given the current token and the window or the context of the previous tokens, we should learn to predict the next token, which is the 513, the target token. That's kind of the idea of how this works. And the transformer as an architecture is great at figuring this out, at taking a context window and then predicting the next token in that context. This is basically some examples also from slides of Andrew about the training process. So in this case, we took Shakespeare data This is the training data. We initialized it, and then we trained the model to generate text that is similar to Shakespeare's text. After 250 iterations of training, the text is basically gibberish. After 500 iterations of training, the text kind of have some words like you'll or your or whatever on, at, but overall words still don't make sense. After 5,000 iterations, we can see a bit more logic into the text. I have been me, thereof my life, and he concludes. So the words are correct, but not the formulation of the sentences. And after 30,000 iteration of training, we got to a point where actually the text resembles the original data. So of course, there's a lot of processing and training that's happening. And it's not easy for us to just train for 1 or 2 iterations and get a good result. That's why this process is very intensive and very expensive, because it requires lots of time and lots of GPUs. And at the end, again, what we get is a base model, not an assistant, meaning that I can give it a sentence and it will complete it. Its job is to complete or to predict the next token. It's not to answer questions or to execute some tasks. So for example, if I say here, write a poem about bread and cheese, that's it. And I say, okay, here's the sentence, continue. It's going to assume that this is a document that is writing some commands, and it's going to say, write a poem about someone who died of starvation. Write a poem about angel food cake. Write a poem about someone who choked on a ham sandwich. So you're going to think that it's just a random request to write a poem. So it's only wants to complete internet documents. It does not care about answering your question or giving you what you need, what you're looking for. So it can be tricked into performing tasks with something that we call prompt engineering. So in this case, instead of saying write a poem about bread and cheese, we can say here is a poem about bread and cheese, and then it's gonna learn to complete it. Because when you start a sentence with here's a poem about bread and cheese, then naturally what's gonna come after that is a poem about bread and cheese. So we're tricking it into performing task, but it's actually not its main goal. Okay. That's the idea of base models versus assistant models. Again, hopefully that's clear. Please ask me questions if you have anything. Moving on. So that's the first step. Now we go to the second stage, which is called supervised fine-tuning. So in this case, we have a base model, and then I can initialize from that base model. I can collect some what you call ideal assistant responses. So a prompt with its own response. Okay, I don't need a lot of information, a lot of data. I need somewhere between 10,000 to 100,000 examples of prompts with response written by contractors, which means that this is high quality data, low quantity but high quality, because it has been viewed by a human. It's good enough, or it has good quality. And then I fine tune that model on this data. So I'm kind of teaching the model to predict the best output from that prompt. And what I end up with is what we call a supervised fine-tuned model, SFT model. Okay, so an SFT model is similar to a base model, but it was fine-tuned on ideal responses. So here's how ideally you should answer when you are asked something like this. Okay, and in this case, it's a much cheaper training because we're not training everything from scratch. So we don't need thousands of GPUs. We need 1 to, let's say, 100 GPU, and we need a couple of days for training. And of course, we can deploy that model after it's done training. So it's a usable model. So for example, here's a prompt. Can you write a short introduction about the relevance of term, blah, blah, blah. And here's a response. So, okay, so we can kind of teach the model how to do that. And Instruct GPT, if you've heard of it, it's one of those fine-tuned model. For example, here, if I say, explain the moon landing to a 6-year-old in few sentences, GPT-3 will say, it's going to complete it, right? GPT-3 is going to say, explain the theory of gravity to a 6-year-old. Explain the theory of relativity to a 6-year-old in a few sentences. So it's going to assume that it's part of a text and it's going to complete the text with this request. Whereas Instruct GPT it's kind of like ChatGPT, right? It's going to understand that it needs to explain the moon landing. And so it's going to say, people went to the moon and they took pictures of what they saw and they send them back to Earth so we can all see them. So it was able to understand from the fine tuning it was given that when someone tells you explain the moon landing, you don't complete it like that. You actually give an explanation. So this brings us to the third stage, which is the reward modeling stage. So in this case, we need to collect some comparisons. Okay, so we take a supervised fine-tuned model, we ask it some questions, and then, as you know, every time we give it a certain prompt, it's going to give us a different answer. So it's going to give us an output that is different. So we collect a couple of these outputs for the same input, for the same prompt. Give me 2 or 3 different outputs. Okay, so around, let's say, a couple of 100,000 to 1 million of these comparisons. Again, it's low quantity, high quality data. And then I build what we call a reward modeling or a reward model system that is capable of predicting in a binary format the quality of this prediction. Okay, so for example, this is the same prompt. Write a Python function that checks if a given string is a palindrome. And this is different output from the AI model, from the supervised fine-tuned model. So I have different outputs. And what I want to do is I want to build a model that can learn to predict the quality of that answer. So which one of those is the best answer? Is it this one or that one or this one? So I give these examples to a human annotator, and I say, rate these answers based on the highest quality to the lowest quality. And then I feed those data back to the system. So the RM model, what its job is basically as follows. It looks at the prompts, which are the blue color tiles, and then it looks at the completion, the actual answer, which are the yellow tokens. And finally, we have the green token, which is the reward. And this is where the humans have annotated. So the humans have decided that the first answer has the highest reward, 1.2, because it was the best. The second one has the lowest reward because it has minus 0.5. And the third one is the second best answer. So we have ranked the answer based on best, good, and poor. So we feed those to the system, and the system will learn how to to predict the reward for every completion. So if I give it a prompt and I give it a completion, it's going to say that's how well this completion is. That's how well the answer is to that question. Okay, so that's the job of the reward model. It's actually a useless model by itself. That's why we cannot deploy this model by itself. Its job is only to assess the quality of the answers that you are getting from the prompt. And then finally, this gets us to the last stage of our training, which is obviously reinforcement learning. You might have heard of reinforcement learning from human feedback, or RLHF. That was exactly what was used in this case, where, again, we collected some prompts with the answers from some contractors, low quantity, high quality. And then we applied reinforcement learning. So we took initialized the model from SFT. So it's a supervised fine-tuned model. And then we used the RM model to predict the quality. So here's how this works. Again, we have the SFT model. We give it the prompt with the completion. Okay. And the RM model learns to predict the reward for that completion. Okay. And then based on that, the reinforcement learning model, the actual model we're training, will learn that, okay, if this model has the highest reward, then I should give more probability to those tokens. So the row tokens of the row first, so the first one, these tokens we have to boost their probability. We have to decrease the probability of the tokens of the second row, and these are okay. So maybe slightly boost these tokens. So it puts a reward function on the tokens to be generated by the model based on what the reward model gave us. Okay, so that way, the final output of the reinforcement learning stage, is basically a assistant model. It's something like ChatGPT or Claude. It's an assistant model where you give it a prompt, it generates multiple versions, it ranks each one using the reward model, and then it learns to predict the best answer based on those rewards. And that's basically how ChatGPT is, right? That's the difference between ChatGPT and a typical GPT or LLM. It's one of them is an assistant, it's a chatting assistant, the other is a purely large language model. I hope this makes sense for everyone. Again, if that's not clear, I'd love to repeat, so please ask me your questions. So now that we've understood a bit how this works, let's talk about the API of OpenAI. So OpenAI has different APIs to tackle different models, starting with their basic model, which is basically, here's a prompt, write a tagline for an ice cream shop, and here's the completion, we serve up smiles with every scoop. So that's the basic API. You give it a prompt, it answers back. So that way, or to implement that in code using the Python code, obviously, we import OpenAI, we specify the API key, which I'm going to show you how to do that. And then you can call the OpenAI.completion.create API endpoint. You specify which model you are looking to use, and then you give it the prompt, which is write a tagline for an ice cream shop. Sorry. Okay. So if you're doing chatting, then you should use the chat completion instead of the purely completion endpoint. Chat completion will basically, you're chatting with an assistant. So in this case, you choose a model like GPT 3.5 Turbo. And then in this case, you have to specify not only the content, but also the role. So initially, we always start with the system role. And the system role is basically what defines the initial prompt for that agent or for that chatbot. In this case, you are a helpful assistant. Then you have the user who said who won the World Series in 2020. Then the assistant or the chatbot replied with Los Angeles Dodgers won the series. And then the user asked where was it played, etc. So there's a context, there's a chat history, and that's how we keep track of it in the messages argument in the API. I'm going to show you all of these in code, but that's basically how it is. It's pretty straightforward. You call a few APIs and then you communicate with OpenAI. Now, before we jump into the hands-on, I want to cover LangChain because LangChain is a very, very, very useful library or framework that's going to allow us to build these conversational agents or apps. So LangChain is a Python library that really helps you leverage LLMs to build custom NLP applications. So you can build basically chatbots with LangChain. You can build summarization and question answering systems. You can build apps that query databases to fetch information and process them. You can build agents that solve specific math or reasoning puzzles. So it's really a diverse framework. Today, we're going to use it to build a chatbot, but of course, you can build much, much more than that. It allows you to chain different steps, different tasks, and different LLMs together as well. And the LangChain has 5 main modules that we're going to cover one by one, starting with the models, right? So LangChain has a module called models that actually converts or contains 3 different models. We have the language models, as I told you, the models that can take a certain text and complete that text. So GPT is a language model. It has also chat models where you can build chatting messages and the history conversations with these assistants. And it also has text embedding models, which are models that can take text and embed them in a vector. So we call them text embedding models. So this is the module of the models. Also, some parameters that we can pass to LLM is basically the engine. So which actual model we're going to use here to generate, what is the engine? For example, GPT 3.5, GPT 4, etc. We can also create or specify the maximum tokens. So that's an argument that controls the length of the generated text. We can also specify a certain stop, which is a stop word. So for example, if you don't want it to generate endless text, you can say stop at this word or stop after this, for example. And there's also an argument called temperature, which controls creativity of these LLMs. So it's a value between 0 and 1, where the higher the value is, the more it's going to result in diverse and unpredictable outputs. And the lower the value is, the more it's going to be predictable and conservative output. So you can control the temperature of that LLM or the answer. Second module we will cover is called chains. And chains is the idea of chaining multiple steps in a certain action. So sometimes you don't want to just send a query for the chatbot or for the LLM and get a text completion back. You'd actually want to do multiple things. So you want to get the user input, you want to format that to the LLM format that it's expecting, and then you want to run the prompt and get the response from the LLM, and then you're going to get the results back and do something else. So that's where chains come in. You can chain multiple things together, and you have built-in chains that are available, like the LLM chain. So in this case, we can import the LLM chain from LangChain, and then we can create something that we call the prompt template. So a prompt template is basically, if you have a prompt that you're always going to use and change a few things, you create a template, and then you just add the thing as a variable. For example, what is a good name for a company that makes X product? So if I'm building an assistant that's going to help you to come up with a name for your company, it's always going to be, give me some good name for a company that does X, that sells ice cream, that sells shoes, whatever. So instead of asking the same question, I build a prompt template where the product is a variable. I then create LLM based on OpenAI. I create an LLM chain. I specify the actual model, and I specify the prompt. So prompt is part of the prompt template. So I create prompt template.from template, whatever this template is. And then I just call the chain and pass in colorful socks. So it's going to take this variable, it's going to fill in the product, and it's going to answer me, what is a good name for a company that does makes colorful socks. So I can create multiple examples without having to repeat all the work. So that's one example of the LLM chain. There's a chain called LLM math chain that, as you guessed it, is focused on solving math problems. So in this case, LLM math chain from LLM, we create a math chain from the OpenAI LLM, and then we can run this query, which is what is 13 raised to the 0.3432 power. We also have the LLM bash chain that allows me to run bash commands, like please write the bash script that prints hello world to the console. So it's going to run that as well. And also you have API chains, where basically it enables your LLMs to interact with APIs and retrieve specific information, like the weather or some specific website that offers some APIs. If you focus on the prompts are super essential for everything to do with NLP and with wait, I think we have a question. So let me answer the question. How do these chains work behind the scenes? Do they query extra model knowledge? Yeah, it depends on which chain you're talking about. So these chains, the LLM math chain or bash chain, they're actually they're built in a way that they leverage a certain LLM model plus some form of extra model knowledge, as you mentioned. Of course, depending on the actual chain. The API chains, obviously, yes, there's an API call embedded. So let's say the weather chain, it uses LLM to understand the query, and then it uses a pure API call to open Meteo website to actually retrieve the results based on some specific JSON format or something. And then it processes it and returns back the answer as you expected. So yeah, hopefully that answers your question. Okay, I was talking about the prompts. Prompts are very important for any NLP application because you have to know how to ask your questions to get the right answer. Of course, in ChatGPT, the answer is only as helpful as the prompt itself. And that's why LangChain provides prompt templates, as I told you earlier, where you can provide a template and then just fill in the different, let's say, products or variables, like in this case, colorful socks. The third module we will cover is called document loaders and utils. So obviously, to build your chatbot or your system, sometimes you need to read data from documents, and that's why this module is very important. It facilitates connecting to sources of data and computation. So you can have, let's say, your data set. Data can be documents on your local device. It can be on the cloud. It can be on Drive. It can be in PDF and images and Excel and HTML. There's a lot of different types of or formats of data. And so this module allows you to load all of that data, whether it's locally or on the cloud, no matter what format it is. You load it. It allows you to transform it. It allows you to create an embedding of each of one of those, and then store it in what we call a vector store, and then finally do the retrieving part. All of those steps are part of the document loaders and utils module. So that's why LangChain is very useful, because you can pretty much connect any type of data to your system and output any type of data. It's very modular in that sense. If you heard of the term vector stores, but you don't know what actually these are, vector stores are a new type of database that have been really becoming trendy lately because of the whole AI boom. So if you know, basically AI, when you feed a certain text into a certain model, it doesn't take the text as it is, right? It converts it into tokens, and then it learns the embedding of that text. And an embedding is basically a vector, a numerical vector that represents the input data, that represents the text. So if ChatGPT wants to look up information, for example, it wants to chat about something, it's basically, it creates an embedding of that information and it saves that into the database. And there are specific types of databases called vector databases that are great at not only storing vectors, but also retrieving vectors. So doing the search, doing the query on these vectors in a very quick and efficient manner. So just like an SQL engine is great at storing data in SQL tables, and then you have the SQL query language to query that data in a quick way. Similarly, vector databases can store and retrieve embeddings. So the idea is that you have your content and you have your application. The content is stored, it's embedded and it's stored in the vector database. And then the application will send a certain query to the embedding model. The model will check the database and then return the results here. And there's a lot of options of vector databases, like the FAISS, the open source vector database. We have Pinecone, Milvus, Chroma, Elasticsearch. There's plenty of other options as well. And all of these are supported by LangChain. And the last module we need to cover is the agents module. So agents are a bit more complicated than typical LLMs, right? So you have your typical chain where you get the user's prompt, you send it to the chain, it gives you the answer, that's it, that's fine. But sometimes you have some applications that require more a chain calls of LLMs, and basically sometimes also tools. So if you've heard of these AutoGPT or AI agents lately, these are systems that you give a goal to, and then they figure out the different steps they need to take to actually achieve that goal. So it's not as simple as write me a poem or give me the name of a company. It's sometimes, this turning into a list of steps and list of tools to be used. And this is where agents are great. So an agent has access to a suite of tools and determines which ones are used which ones to use depending on the user input. So basically, it receives the user input. That's the first thing. It decides which tool to use. If there's a need to use a certain tool, it calls that tool, records the output, then decides on the next step. Is this enough? Can I answer back the user, or I need to do some other things? If it realizes that actually I still need to decide on a tool and use it, it's going to repeat the steps of 3 and 4 until finally it says, okay, I'm ready to answer the user. For example, let's say I ask about, I don't know, I'm going on a trip, and when is the best time to travel, for example, to Paris? It's going to decide that I need to check the weather, for example, right? it checks the weather, it gets the output, and then says, okay, I need to also check the booking cost or travel cost. So it goes to booking.com or Expedia or whatever. It checks the data or the flight and accommodation and details. So there's a lot of steps involved before it can answer me that the best time to travel is between this or that or whatever. So that's the idea behind agents. And LangChains allow us to build very smart, very advanced agents that can basically do a lot of tasks in that way. So now I'm going to quickly show you the logic to build your own chatbot, and then we're going to jump into the Google Colab and see things in action. So to create your own chatbot, we don't just need to, if you need an AI that can answer any questions about anything else, then of course you can just use OpenAI's ChatGPT, and it's going to answer you about anything. But when we say your own chatbot, we mean a chatbot that can answer data about your own company, your own products, your own services, etc. So in that way, you have your documents, you have your own data, and then you use document loader to load those documents. You split them into different chunks using the text splitter. That would be the logic. You then embed them using a vector or a embedding model, and then you save those embedded chunks into a vector store. And then basically, when the user is asking a query, the query is embedded. We convert it to an embedding. It goes to the vector store to do a similarity search. We find the most relevant embeddings that can match the user's query. And then those chunks are returned back to the LLM, where the LLM actually computes the final response and returns back to the user. Okay, so that's kind of the idea that you need to follow to build your own chatbot. So let me jump on the hands-on example now. I'm going to show you things in action. You should have received the PowerPoint and also this Colab file in the Drive folder. If you did not receive it, then let me know, and I'll send you the link as well. I assume everyone here knows how to use Google Colab. If you have any questions on that, also let me know. I'm going to start by briefly running some basic things. So let's start by installing OpenAI. Okay, so pip install OpenAI just to install the library. And then you have to define your API key, because you need the key to actually call the API. Okay, that's not important. So import OpenAI, and then OpenAI.API key equals, and this is where you have to insert your own API key. You can get that by going to platform.openai.com and then creating a new key. So I'm gonna take my key from here. I'm gonna paste it here. So that's my API key. And then to show you a simple query, I create a messages array that says role system, and the content is you are an intelligent assistant, you are extremely good at making jokes. That's what I would like to initialize my assistant chatbot as. And then let's say tell me a smart joke, make it rhyme. That's my query or my prompt. I append it to a message that says content is the message and the role is the user. So the user is asking that role. And then I can call OpenAI.chatCompletion.create. This is the model. These are the messages, and that's the temperature. So create the chat. Okay, so apparently they changed the chat completion, which is basically we have to actually update the code. Let me just quickly check. Yeah, I will send you the link right now. Let me just copy that and paste it here. I think everyone should be able to see. I'm gonna share it again in the chat just in case you guys could not see that. So this is the folder that has the collab. Forget these two documents, we'll discuss them later, and also has this presentation as well. So let me look at just what they did with the changes, because it's now okay. So clients completion.create. Oh, we have to create an OpenAI. So basically, let's do this. Client equals open AI, and then client dot chat completion. Hopefully this works. From OpenAI, import OpenAI. Actually, let's do it right here. Okay, so API key equals, let's give it that. So I'm sorry for this. Set completions. Nope. Okay, so let's check. It's the chat.completions. Okay. Okay. So, okay, so now that's a new format. So we create a client, OpenAI client, and then client.chat.completions that create. Everything else should work. So hopefully now the syntax is the same. If I look at the chat.choices, .message.content, you can see that the reply, I asked it to tell a smart joke and make it rhyme. And it says that why did the mathematician always bring a ladder? Because he wanted to reach the highest rung and solve equations that others floundered. So this is the joke, right? If you want to look at what the chat response includes, okay, usually it used to kind of put it into a JSON object, but basically here's what it includes. So you have the ID of the request, right? You have the object, the actual set completion object, which is this called choices. So choices here is a list of completion objects. So sometimes it's only one, sometimes it can give you multiple completion options. Then you have here the finish reason stop. So finish reason is why the model stopped generating text, either because it has finished to generate the whole sentence or because it has reached the maximum tokens limit. Then you can see here the message that includes the content, what the mathematician bring a ladder, etc. And then you can see the timestamp for the creation. You can see the model that was used, and you can see the usage completion. This is important. So you can see at the end that it used 28 tokens, the completion tokens. The prompt tokens is 35, and total tokens is 63. So why is this important? Because you pay per token for the usage of the API. So you want to be able to track technically how much was this query costing you, right? So you can calculate that based on adding up the tokens. That's a very simple way of calling OpenAI. Now, I'm going to also give you a basic of LangChain before we dive into building our own chatbot. So in this case, we have to install LangChain by calling pip install LangChain. And then we import from LangChain the prompt template, the chat OpenAI, and the LLM chain. So we want to chat with the OpenAI models, and we want to also build the LLM chain. Then we create the summary template. So given the information about a person, I wanted to create the following. So the first template is the information object. And the following is I wanted to create a one-liner short summary and also X number of interesting facts about them. So I define the summary template. I create a prompt template based on that summary template. And then I create an LLM based on chat OpenAI, where the temperature is 0, the name model is GPT 3.5, and this is the API key. And then I wrap it up in LLM chain. So this is the chatbot, which is called LLM. And then the chain is this LLM with this prompt template. And once I define the chain, I can just call chain.run and provide the information. So I got here some information about Elon Musk from Wikipedia, literally like the details about Elon Musk. And then to run the chain, I'm gonna say the number is 3. So I want you to use this information about Elon and this number to generate, again, remember the prompt, a one-liner, and then 3 interesting facts about Elon Musk. So when I run here, chain.run, I get the text. Okay, it's going to take some time because it's calling the API of OpenAI. And now if I print the text, it's going to say, okay, Elon Musk is a business magnate, investor, and entrepreneur known for his business, for his leadership roles in companies like SpaceX, Tesla, and Twitter. This is the one-liner. And then 3 interesting facts about Elon Musk. Musk is the founder and CEO of SpaceX. He's also the CEO and product architect of Tesla, etc., etc. So these are 3 facts. And now I can fill in any information and any number of facts, and it's going to give me that. So for example, Steve Jobs, this is the Wikipedia article of Steve Jobs. I'm going to run that, and I'm going to say, run and give me 2 information or 2 interesting facts about Steve Jobs. So of course, it summarizes in a one-liner, and then it says, interesting facts about Steve Jobs, 1, 2, etc. So that's kind of the idea of how we were able to call OpenAI from LangChain. Okay. Hopefully this is clear for everyone. If you have any questions, also let me know. Now we're gonna kind of combine everything to build our own chatbots with our own documents using LangChain and OpenAI. And this is where these documents come into play. So as I told you, if I open up this drive again, you will have 2 documents. One of them is called AI Bootcamp. It's just a text file that contains information about a program that we have at Zaka called the AI Bootcamp. So it has details about Zaka, what is Zaka AI Bootcamp, talking about that bootcamp, program overview, some details about the program itself. Okay, I'm gonna use those knowledge to feed the chatbot to answer questions about that. We have a question here. Okay, so the information variable is kind of a weird, in a weird place. No, it translates to, here is some Elon Musk. Yeah. I mean, technically you're right. It can be placed in a better way. For example, we can say, given the information about a person, and then we can say here, information. Sorry, you can do it like that. But the cool thing is that these LLMs, they have really a good understanding of text. So it doesn't really confuse them when you put it like that. But yeah, we can basically have a best in a better way. So that's a good point. Okay, so let's I was saying this, we're gonna use this AI Bootcamp text file to teach it, to give it to the AI chatbot so it can answer questions about the bootcamp. And then also to test another thing, I also have a PDF called AI Certification. It's a different program, and I put the content of it in a PDF with some details and detail, whatever, graphics. And then also we're gonna feed that to the system so it can learn from it as well. So I'm showing you 2 different types of data, text files and PDFs. Of course, it has other data loaders as well. So if you go actually to LangChain documentation, I'm gonna show you quickly data loaders. So not the chains, but actually where is it? It's not document loaders. Here it is. Okay, so you can see, for example, CSV, file directory, HTML, JSON, Markdown, PDF, and then I think there's also a huge list of custom. They changed where they were hiding it, but actually, yeah. So there's a lot of things that you can import in terms of types of data, right? So we're trying right now just to go with PDF and text. So moving on from LangChain.document loaders, import text loader, and then text loader. Actually, I have to upload the AI Bootcamp here. Wait, AI_Bootcamp, and then let's also upload the AI certification. So AI certification, that's it. Okay, so we have now the 2 files here. I'm loading the AI Bootcamp and the text loader, and then that's the text itself. And then I installed PyPDF to read the PDF file, I import from LangChain.document loaders the PyPDF loader, and then I specify this file, the PDF file, and I load it into a different data object. So I have now the bootcamp text, which is the text of the bootcamp, and then I have the data underscore PDF, which is the content of the certification one. So I combine them into a documents array. And now I have to chunk them because it's a huge text. I cannot just save everything. We have to put them into chunks, and then we have to embed every chunk into an array, into a vector. So I import the character text splitter. I then initialize it and then call text splitter.split documents. And of course, it's going to split them based on this size, 512 tokens, with an overlap of 40 tokens. That's basically how it's going to decide to chunk them. If you ask me why I decided that number, there's no reason. You can reduce it or improve it or whatever you want to do with it. But basically, that's a fair enough number. So we ended up with 17 different documents, right? Different split chunks. And if I select the split documents or the chunk at index 5, you can see that this is what the document says. Bootcamp format, the virtual AI bootcamp engages participants. So it selected a part of the bootcamp text and it put that into a document, right? So it's splitting the huge text into small chunks to be able to use it for indexing. Then we have to import the OpenAI embeddings. So we're going to call the embeddings model of OpenAI, give them the chunk, and return a vector embedded of that text. So in this case, embeddings equals OpenAI embeddings. I specify the OpenAI key. I install ChromaDB as the vector store. So I'm doing all of this because eventually I'm gonna take a chunk, give it to OpenAI embeddings, take the embeddings of that, save it into a certain vector store. So in this case, I'm gonna use ChromaDB as my vector store. So from LangChain.vector stores, I import Chroma because that's the one I'm using. And then I create the Chroma by saying from documents, split documents, embeddings. And this is what's going to do the whole magic, right? The from documents function will take the split documents, will take the embeddings, will save it as an embeddings for every vector. And we have a okay. So we have to import the tick token. So this is basically the library that is possible for tokenizing the words. Okay, hopefully that works, or we have to restart the runtime. Okay, perfect. So now we have stored in our vector store, and if you look here, I think we should be able to. Oh, maybe it saved it in the hidden temporary file, but you should have like a local DB that's storing these embeddings. So now when I say, let's say I have a query, what is Zaka AI Bootcamp? I go to the vector store on .similarity search on that query. So give me all the chunks that are similar to that query. It gave me 4 documents. And if I print them, you can see here, what is Zaka AI Bootcamp? This is the first chunk. So actually, let's print the first one by itself. So that's the document, right? That's the chunk that is most relevant to this query. Okay, from the vector store. We're just doing vector store in this case. We're not doing any LLM process, but I'm showing you how the vector store understands your query and gives you back the relevant documents. So now to do it inside of LangChain, we're going to create a retriever. Okay, so vector store.as retriever, type similarity, and give us maximum the 2 closest documents. And then I create a conversational retrieval chain. So in this case, it combines the chat history, and that's important when you're doing a chatbot. There's a lot of different chains that you can use from LangChain, but you need to use something that's going to be holding the history of the conversation. So in this case, the conversational retrieval chain provides the chat history component. We import that chain, we import chat OpenAI, and then we create again the OpenAI connection as the LLM. We create a conversational retrieval chat from that LLM. We pass it the LLM and the retriever. Why we do that? Because if I ask that question about let's say Zaka, it's gonna go to the retriever and extract the information from the vector store. But if I ask it a question about anything in general, then it's gonna go to the OpenAI to ChatGPT model, and it's gonna give me the answer. If it did not find it in the vector store, that's why we need a language model. So now that we've set up everything, we can actually start by chatting with it. So chat history is empty. Query is where is a Zaka AI bootcamp, and then we've built it in a chain where it takes the question and the chat history. That's how you. That's the type of the message you submit to the chain. Because it's a conversational retrieval chain. So it takes the query and takes the history, and then it returns the answer. So if I print that, okay, it's gonna go query that and give me the answer back. So it says Zaka AI Bootcamp is a program offered by Zaka, a startup focused on AI education and consultancy. The bootcamp is designed to introduce participants to the field of artificial intelligence and provide them with necessary knowledge and skills to get started, blah, blah, blah. So it knows how to answer my question. If I look at the result object itself, you can see that it has the question, the chat history, and the answer. It's a pretty simple object as a to be returned. Now, I have to submit another follow-up question, right? So I have to append my chat history. So I take the chat history, this empty array, I append it with the query and the result, and then ask it a new question, which is, are there any prerequisites to join? Notice how I did not mention to join which program. I just said, are there any prerequisites to join? But because I'm actually asking it after the initial question, which is what is Zaka AI Bootcamp, it will know that I'm talking about the bootcamp, right? So you can see here that the given context does not provide information about the prerequisites to join Zaka AI Bootcamp. So it knows that I'm talking about the AI Bootcamp, but it wasn't not able to find the actual information if there's any prerequisites or not. If you look at the result object, there are now the question, of course, the prerequisite, and then the chat history that includes the initial question with the initial answer, and then the final answer. So moving on, let's say I ask it now a non-Zaka question, okay, which is basically, who is Elon Musk? So I add this into the chain, chat history, and I query the answer. It says Elon Musk is a well-known entrepreneur and business magnate, blah, blah, blah. So you know that it did not rely on the vector store because I have no information about Elon Musk. It actually went to the actual LLM and asked the LLM itself. So that's the idea. So if you want to make things easier, we're going to define here a function called askBot. It's going to take a query and chat history. It's going to do the same steps. So append the history, ask it to the chain, reply back. So let's define this, and now let's chat with it. So how long is this program? Okay, I'm going to ask it like that. It says the duration of Zaka AI Bootcamp is not mentioned in the given context. I think there's something wrong because it is given, but let's try something else. Let's try to ask directly the vector store here. So let's actually place that. Okay, wait. How long is the AI bootcamp? Okay, so if you print the documents, let's print all of them. Just I want to double check. Do we have that information or not? Wait, actually, let's make something smart. So we have this bootcamp, which is a text. Let's say, what are the topics covered, right? Because we say we have here the topics covered include, etc. So if I ask it, what are the topics covered, it should be able to answer me, right? So let's see here. What are the topics covered? You see, topics covered in the Zoghbi AI program are machine learning, deep learning, computer vision, natural language processing, and time series analysis, which is correct. It has taken them from here. Let's say I want to talk to you about the duration. It says duration, but it was not able to see it. Maybe let's talk about the bootcamp outcomes. What are the bootcamp outcomes? Okay, so it was able to answer me back. So that brings us to the end of this workshop. Of course, this was a very basic introduction of how we can leverage these models, but you can dive more into the different integrations, the data store, the history of the chatting history, and different features as well to make it more robust. Are there ways to mitigate information that is unfortunately split among two chunks? There are actually. It depends on the chunk size and the overlap size. You can increase the overlap size to make sure that they are overlapped. And you can sometimes change the way you format your text when you give it to these systems. So it includes the data in a better way. But usually, I think because I didn't really format the data, I just dumped everything here. So you can see there are sometimes different formatting issues or something like that. So you can increase the chunk size, you can increase the overlap size, and hopefully this would solve it. So yeah, so that's the idea. I highly encourage you to go to LangChain's documentation. There's a lot of different classes that you can use to build your chatbots or basically conversational agents. So use a lot of that as well. And yeah, hopefully you enjoyed that. If you have any questions, let me know. And thank you all for joining today. Hopefully this was useful.
All right. Thank you, Christophe. That was very interesting. And thank you everyone for participating and watching the tutorial.